How the Milky Way compares to other spiral galaxies. We live inside a spiral galaxy. From our vantage point on Earth, embedded within one of the Milky Way's spiral arms about 26,000 light-years from the galactic center, we see our home galaxy edge on as a misty band stretching across the night sky. This inside perspective makes it challenging to understand what our galaxy really looks like and how it compares to the countless other spiral galaxies we observe throughout the universe. For centuries, we didn't even know the Milky Way was a galaxy, one island of stars among billions. It wasn't until the 1920s that Edwin Hubble proved that spiral nebulae were actually distant galaxies like our own. Since then, astronomers have studied thousands of spiral galaxies, measuring their properties, mapping their structures, and understanding their diversity. Today, we're comparing the Milky Way to other spiral galaxies. We'll explore how our galaxy measures up in terms of size, mass, structure, star formation, and evolution. We'll see where the Milky Way is typical, where it's unusual, and what this tells us about galactic evolution and our place in the cosmic landscape. This is the story of understanding our home galaxy by seeing it reflected in its countless cousins across the universe. Defining spiral galaxies. Before comparing the Milky Way to other spirals, let's define what makes a galaxy a spiral galaxy. Spiral galaxies are disk-shaped systems with several key features. First, they have a flat, rotating disk containing stars, gas, and dust. This disk is where most star formation occurs. Second, they display spiral arm patterns, regions of enhanced density where stars, gas, and dust concentrate. Third, most spirals have a central bulge, a spheroidal concentration of stars at the galactic center. Many also have a bar, a rectangular structure of stars extending through the nucleus. Edwin Hubble classified galaxies in the 1920s, creating the tuning fork diagram that astronomers still use. Spiral galaxies divide into two main categories: ordinary spirals, designated S, and barred spirals, designated SB, which have prominent bars through their centers. Both types are further classified by how tightly wound their spiral arms are and how prominent their central bulges appear. SA and SBA galaxies have large bulges and tightly wound arms. SC and SBC galaxies have small bulges and loose open arms. SB and SBB galaxies fall in between. The Milky Way is classified as SBBC, a barred spiral with a modest bulge and moderately open spiral arms. This classification comes from careful observations combining what we see from inside with what we infer from comparing to external galaxies. Spiral galaxies make up about 60% of galaxies in the nearby universe, though this fraction was different in the past when galaxies were still forming and evolving. They're sites of ongoing star formation, contain significant amounts of gas and dust, and display the complex interplay between gravity, rotation, and gas dynamics that creates spiral structures. Understanding where the Milky Way fits among spiral galaxies helps us understand whether our galaxy is typical or unusual, which in turn affects how we think about galaxy formation, stellar evolution, and even the likelihood of planetary systems and life elsewhere in the universe. Size and mass. Let's start with basic metrics. How big is the Milky Way, and how does it compare in size and mass to other spiral galaxies? The Milky Way's visible disk extends to about 100,000 light-years in diameter, though the exact edge is difficult to define since stars gradually thin out rather than stopping abruptly. The stellar disk, where most stars reside, is about 1,000 to 2,000 light-years thick. Our Sun orbits at approximately 26,000 light-years from the galactic center, roughly halfway out in the disk. The total stellar mass of the Milky Way is approximately 60 billion solar masses, meaning if you added up all the stars in our galaxy, they'd equal about 60 billion times the mass of our Sun. Including gas, dust, and dark matter, the total mass within the visible disk reaches several hundred billion solar masses, with estimates varying depending on measurement method. How does this compare? The Milky Way is a large spiral galaxy, but not exceptionally so. It falls into the category of L-star galaxies, galaxies with luminosities near the characteristic luminosity L, where the galaxy luminosity function turns over. This makes the Milky Way reasonably typical of bright spirals. Consider some comparisons. The Andromeda Galaxy, M31, our nearest large neighbor, about 2.5 million light-years away, is somewhat more massive. Andromeda contains roughly 1 trillion stars, compared to the Milky Way's estimated 200 to 400 billion stars, and its disk diameter is about 220,000 light-years, nearly twice the Milky Way's size. Andromeda is definitely the bigger sibling in our local group. The Triangulum Galaxy, M33, the third largest in the local group, is considerably smaller than the Milky Way. M33 has a mass of about 50 billion solar masses, less than the Milky Way, and a diameter of roughly 60,000 light-years. Looking beyond our local group, NGC 6946, sometimes called the Fireworks Galaxy due to its high supernova rate, has similar size to the Milky Way, about 40,000 light-years in radius. The Pinwheel Galaxy, M101, is substantially larger, with a diameter of 170,000 light-years, nearly twice the Milky Way's size. Among all spiral galaxies, sizes vary enormously. Small spiral galaxies might be 20,000 light-years across, while giant spirals can exceed 250,000 light-years. The Milky Way falls comfortably in the upper middle range, larger than most spirals, but not among the true giants. Mass follows a similar pattern. Typical spiral galaxies have stellar masses ranging from 10 billion to 100 billion solar masses. The Milky Way, at around 60 billion solar masses, sits towards the upper end of this range. Most spiral galaxies are smaller and less massive than ours, but substantial populations of larger spirals exist. This positioning matters for understanding galactic evolution. Larger, more massive galaxies have deeper gravitational wells, retain gas more effectively, experience different merger histories, and evolve along different pathways than smaller galaxies. The Milky Way's size places us in a regime where we're massive enough to have undergone significant evolution, but not so massive that we're dominated by merger history like giant ellipticals. Structural features. Beyond overall size, spiral galaxies vary in their structural components. How does the Milky Way structure compare? The Milky Way has a central bar extending about 27,000 light-years from end to end, roughly 10,000 light-years wide. This bar rotates as a solid structure, completing a rotation every few hundred million years. The bar's existence was confirmed in the 1990s through infrared observations that could peer through obscuring dust. Bars are common in spiral galaxies. Surveys suggest that roughly 2/3 of spiral galaxies have bars, with the fraction possibly even higher. The Milky Way's bar is fairly typical in size and strength compared to other barred spirals. Bars play dynamical roles. They transport gas inward towards the galactic center, potentially fueling star formation and feeding central supermassive black holes. They also heat the stellar disk, thickening it through gravitational interactions. The presence of a bar affects orbital dynamics throughout the galaxy. The Milky Way's central bulge is relatively small compared to its disk, a characteristic of late-type spirals. The bulge has a boxy or peanut shape, likely related to the bar structure. This is common. Many barred spirals show box-peanut bulges when viewed edge-on. Some spirals have classical bulges, dense spheroidal concentrations of old stars formed early in galactic history through rapid star formation or merger events. Others have pseudo-bulges, disk-like structures built gradually through bar-driven gas inflow and subsequent star formation. The Milky Way appears to have a composite bulge with both components. The Milky Way has 4 major spiral arms, though the exact number and structure remain debated due to observational difficulties. From inside the disk, distinguishing between major arms and minor spurs is challenging. Observations in radio, infrared, and other wavelengths gradually reveal our galaxy's spiral structure. Compared to other spirals, the Milky Way's arm structure appears moderately developed. Some spirals, like M51, the Whirlpool Galaxy, display dramatic, well-defined spiral arms. Others show more flocculent structure, with fragmented, poorly defined arms. The Milky Way falls between these extremes. We have clear spiral arms, but not the most dramatic examples. The pitch angle, how tightly wound the arms are, varies among spirals. Tightly wound arms have small pitch angles, while open arms have large pitch angles. The Milky Way's arms have pitch angles around 10 to 15 degrees, typical for SB/SC type spirals. The Milky Way also has a stellar halo, a roughly spherical distribution of old stars and globular clusters extending well beyond the disk.
The halo structure preserves fossil records of the Milky Way's formation and merger history. Comparing stellar halos across spirals revealed diversity. Some galaxies have extended, massive halos, indicating violent merger histories. Others have minimal halos, suggesting quieter evolution. The Milky Way's halo is fairly typical, consistent with a moderate merger history. We've experienced some mergers, but weren't built primarily by major mergers like elliptical galaxies.
Star formation rate. One of the most important characteristics of spiral galaxies is their star formation rate, how many solar masses of new stars they create per year. The Milky Way currently forms stars at a rate of approximately 1 to 2 solar masses per year. This means every year enough gas collapses and ignites to create stars totaling 1 to 2 times the Sun's mass. Over millions and billions of years, this steady production builds up stellar populations. How does this compare? The range among spiral galaxies is enormous. Quiescent spirals with depleted gas supplies might form only 0.1 solar masses per year. Vigorously star-forming spirals can exceed 10 to 20 solar masses per year. Starburst galaxies undergoing episodes of extreme star formation can reach 100 solar masses per year or more, though these are temporary phases. Among normal spiral galaxies not undergoing starbursts, the Milky Way's star formation rate is fairly typical. It aligns with expectations based on our galaxy's mass and gas content. Empirical relationships like the Kennicutt-Schmidt law relate star formation rate to gas density, and the Milky Way follows these relationships. The Triangulum galaxy, M33, forms stars at roughly 0.4 solar masses per year, less than the Milky Way, but consistent with its smaller mass. The Andromeda galaxy forms stars at about 0.4 solar masses per year as well, surprisingly low given its larger mass. This suggests Andromeda has a lower gas fraction or less efficient star formation than the Milky Way. NGC 6946, the Fireworks galaxy, lives up to its name with a star formation rate around 4 to 5 solar masses per year, several times higher than the Milky Way, despite similar size. This higher rate is supported by abundant gas and possibly enhanced by interactions with companion galaxies. M51, the Whirlpool galaxy, forms stars at roughly 3 to 4 solar masses per year. Its interaction with a companion galaxy, NGC 5195, likely enhances star formation by compressing gas in the disk. Star formation rates correlate with gas content. Galaxies with more molecular hydrogen form more stars. The Milky Way contains approximately 2 billion solar masses of molecular hydrogen, concentrated in the spiral arms and inner galaxy. This gas reservoir sustains ongoing star formation. Star formation efficiency, the fraction of gas converted to stars per unit time, also varies. Some galaxies convert their gas rapidly, while others form stars more slowly. The Milky Way's efficiency is moderate. At current rates, our galaxy would exhaust its gas supply in a few billion years if not replenished by accretion from the intergalactic medium or satellite galaxies. The distribution of star formation also matters. In the Milky Way, star formation concentrates in spiral arms, particularly in giant molecular clouds. The galactic center has higher star formation surface density, though it represents a small fraction of total area. The outer disk has lower star formation rates. This radial gradient in star formation is common among spirals. Central regions with higher gas density form stars more actively. Some spirals show ring-like structures of enhanced star formation, often associated with bars or resonances in the disk. Metallicity and chemical evolution. Galaxies aren't made purely of hydrogen and helium. Stars produce heavier elements, metals in astronomical terminology, and disperse them through supernova explosions, enriching the interstellar medium. This metallicity evolution tells us about a galaxy's star formation history.
The Milky Way shows a metallicity gradient, higher metallicity in the inner galaxy, lower in the outer regions. The solar neighborhood at 26,000 light-years from the center has roughly solar metallicity by definition. Moving inward, metallicity increases. Moving outward, it decreases. This gradient reflects inside-out formation. The inner galaxy formed stars earlier and more rapidly, building up metals quickly. The outer galaxy formed slower with less metal enrichment. This pattern is seen in many spiral galaxies. Compared to other spirals, the Milky Way's metallicity is fairly high, consistent with being a large, evolved spiral that has undergone substantial star formation. Smaller, less massive spirals typically have lower average metallicity because they've formed fewer stars and experienced less chemical enrichment. The relationship between galaxy mass and metallicity, the mass-metallicity relationship, is well established. More massive galaxies are more metal-rich. The Milky Way fits this relationship, showing the expected metallicity for its stellar mass. However, scatter exists around this relationship. Some galaxies are more metal-rich or metal-poor than average for their mass. Factors like star formation history, gas inflow and outflow, and merger history affect chemical evolution. The Milky Way's bulge is metal-rich, with some stars exceeding solar metallicity. The disk spans a range from metal-poor halo stars to metal-rich young stars. The stellar halo is very metal-poor, containing some of the oldest stars in the galaxy with metallicities less than 1% solar. Comparing metallicity distributions across different galactic components insights into formation history. The Milky Way's patterns suggest a complex history with early rapid bulge formation, gradual disk assembly, and accretion of metal-poor satellites contributing to the halo. Some spirals show unusual metallicity patterns. NGC 5457, or M101, has higher metallicity in certain outer regions than expected, possibly due to interactions redistributing enriched material. Such anomalies reveal specific events in galactic histories. Alpha element abundances, elements like oxygen, magnesium, and silicon produced primarily in core collapse supernovae, provide additional constraints. The Milky Way shows alpha enhancement in its oldest stars, indicating rapid early star formation when core collapse supernovae enriched before Type 1a supernovae contributed iron. This pattern appears common among large spirals. It reflects the typical timescale for Type 1a supernovae, which require time for white dwarfs to accrete matter and explode, compared to core collapse supernovae, which explode shortly after massive stars form. Rotation and dynamics. Spiral galaxies rotate, and their rotation curves, how orbital velocity varies with distance from the center, reveal much about their mass distribution, including dark matter. The Milky Way's rotation curve is relatively flat outside the central regions. At the Sun's position, orbital velocity is about 220 kilometers per second. This velocity remains roughly constant or decreases slowly out to the edge of the disk. This flat rotation curve indicates that mass continues to increase with radius, evidence for an extended dark matter halo. If the Milky Way contained only visible matter, the rotation curve would decline with radius following Keplerian orbits, similar to how planets orbit the Sun. The flat curve requires a dark matter halo extending far beyond the visible disk. This pattern is universal among spiral galaxies. Nearly all show flat or slowly declining rotation curves at large radii. The dark matter problem was first recognized through galaxy rotation curves, and it remains one of the strongest pieces of evidence for dark matter's existence. The Milky Way's maximum rotation velocity, about 220 kilometers per second, places it in the middle range of spirals. Small dwarf spirals might have rotation velocities of 50 to 100 kilometers per second. Large spirals can exceed 300 kilometers per second. The rotation velocity correlates with total mass. More massive galaxies rotate faster. The Milky Way completes one rotation at the Sun's position approximately 225 million years, a galactic year. This rotation period varies with radius. Inner regions rotate faster in absolute terms but have shorter orbital periods. Outer regions rotate at similar velocities but take longer to complete orbits. Differential rotation, the variation of orbital period with radius, creates and maintains spiral arms through density wave theory. Material doesn't orbit at fixed radial positions but moves in and out of spiral arms as it orbits. Arms are regions where density temporarily increases, not fixed structures rotating with the disk. The Milky Way's spiral arm pattern and bar rotation couple in complex ways. The bar's pattern speed, how fast the bar rotates, differs from the rotation speed of material in the disk. Resonances occur where orbital periods match the bar's pattern period, creating structures like rings or gaps. Compared to other spirals, the Milky Way shows typical dynamic properties. Our rotation curve shape, pattern speeds, and resonance structures match theoretical predictions and observations of other galaxies. However, detailed dynamics vary. Some spirals show stronger warps, bending of the disk out of the plane, likely due to tidal interactions with satellites. The Milky Way has a modest warp in its outer disk. Some galaxies show lopsidedness, asymmetry in mass distribution. The Milky Way appears reasonably symmetrical. Studies of stellar kinematics, how stars move, reveal additional complexity. Stars don't orbit in perfect circles. They have random velocities creating velocity dispersions. Older stars have higher
velocity dispersions, having been heated by gravitational interactions over time. The Milky Way's stellar velocity dispersions are typical for spirals. Young disk stars have low dispersions, moving in nearly circular orbits. Old thick disk and halo stars have high dispersions, moving on more eccentric orbits. Satellite galaxies and environment. No galaxy exists in isolation. Most galaxies have satellite galaxies orbiting them and exist within larger cosmic structures. How does the Milky Way's environment compare? The Milky Way has numerous satellite galaxies. The most prominent are the large and small Magellanic Clouds, visible from the southern hemisphere as diffuse patches. These are dwarf irregular galaxies orbiting the Milky Way at distances of about 160,000 and 200,000 light-years respectively. Beyond the Magellanic Clouds, the Milky Way has dozens of known satellite dwarf galaxies, most discovered in recent years through systematic surveys. These include ultra-faint dwarfs like Cygay 1 and 2, which contain only thousands of stars and are the least luminous galaxies known. Compared to other large spirals, the Milky Way's satellite system appears fairly typical. The Andromeda Galaxy has a similar number of known satellites, including M32 and M110 as prominent examples. Both galaxies likely have additional ultra-faint satellites yet to be discovered. The number of satellite galaxies creates an interesting puzzle. Cold dark matter simulations predict hundreds or thousands of dark matter subhalos orbiting galaxies like the Milky Way, but we observe only dozens of luminous satellites. This is the missing satellites problem. Possible solutions include that many predicted subhalos failed to form stars and remain dark, that supernovae and other feedback processes prevented star formation in low-mass halos, or that dark matter properties differ from cold dark matter predictions. Observationally, many ultra-faint satellites likely remain undiscovered due to their extreme faintness. Satellite interactions affect host galaxies. The Magellanic Clouds gravitationally perturb the Milky Way, potentially triggering star formation and influencing disk dynamics. Evidence suggests the Magellanic Stream, a trail of gas stripped from the Magellanic Clouds, provides fuel for future star formation. Major mergers, collisions with galaxies of comparable mass, transform galaxies dramatically. The Milky Way hasn't experienced a major merger in billions of years, which is why we retain our spiral structure. Evidence from stellar streams and the stellar halo indicates we've accreted numerous smaller satellites, but no recent major mergers. However, the future holds a major merger. The Andromeda Galaxy is approaching the Milky Way at about 110 kilometers per second.
In approximately 4.5 billion years, the two galaxies will collide and merge, forming a large elliptical or lenticular galaxy. This merger will fundamentally transform both galaxies. Not all spirals face this fate on such timescales. The Milky Way-Andromeda merger is a consequence of our local group environment. In different environments, isolated regions, or the outskirts of galaxy clusters, merger timescales differ. The Milky Way resides in the local group, a small collection of about 80 galaxies spanning roughly 10 million light-years. This environment is fairly typical. Many spiral galaxies exist in small groups rather than rich clusters. Group environments allow spirals to retain gas and continue star formation, unlike cluster environments where ram pressure stripping and harassment can quench star formation. Isolated spirals exist as well, though they're less common. These field galaxies evolve without close interactions. The Milky Way's group environment represents the most common setting for spiral galaxy evolution. The central supermassive black hole. Nearly all large galaxies harbor supermassive black holes in their centers. The Milky Way is no exception. Sagittarius S*, the supermassive black hole at the galaxy's center, has a mass of approximately 4.3 million solar masses. This measurement comes from tracking the orbits of stars near the galactic center, which reveal the central mass through Kepler's laws. How does this compare? There's a well-established relationship between black hole mass and the properties of the host galaxy's bulge. More massive bulges harbor more massive black holes. The Milky Way follows the M-sigma relationship, relating black hole mass to bulge velocity dispersion, and the M-bulge relationship, relating black hole mass to bulge stellar mass. The Andromeda Galaxy's central black hole is more massive, roughly 100 to 200 million solar masses, about 25 to 50 times larger than the Milky Way's. This aligns with Andromeda's larger bulge mass. Smaller spirals have smaller black holes. M33, for example, may have a much smaller black hole, though it's difficult to detect due to low mass and activity level. The black hole's activity level matters too. The Milky Way's black hole is currently quiescent, not actively accreting large amounts of material. Occasionally, stars or gas clouds pass close enough to be disrupted, causing brief flares, but generally, Seg A* is quiet. Many spiral galaxies have similarly quiescent black holes. However, active galaxy nuclei, AGN, galaxies with actively accreting black holes are common. These AGN emit tremendous energy across the electromagnetic spectrum, often outshining their entire galaxy. The Milky Way was likely more active in the past. Evidence from X-ray echoes and gamma-ray bubbles suggests past episodes of higher activity. The Fermi bubbles, giant lobes of gamma-ray emission extending above and below the galactic plane, may result from past outbursts from Seg A*. Comparing across spirals, black hole activity correlates with gas availability and merger history. Galaxies with more gas or recent mergers show higher AGN fractions. The Milky Way's current quiescence reflects our relatively undisturbed recent history and modest gas supply near the galactic center. The future Milky Way-Andromeda merger will dramatically affect both black holes. As the galaxies merge, the central black holes will sink toward the center of the merged system, eventually forming a binary. This binary will emit gravitational waves and ultimately merge, creating a single supermassive black hole with mass around 100 to 200 million solar masses. Where the Milky Way is unusual. While the Milky Way is broadly typical of large spirals, some features are noteworthy or potentially unusual. First, our perspective. We observe the Milky Way from within its disk, making certain measurements difficult. We cannot easily photograph our galaxy's face-on spiral structure as we can for external galaxies. This inside view presents challenges, but also opportunities. We can study individual stars, star clusters, and small-scale structures in detail impossible for distant galaxies. Second, our solar system's location is fairly typical, in the disk, partway out, in a region between spiral arms. This is probably the most common type of location in spiral galaxies. Being in a spiral arm would subject us to higher radiation from massive stars and supernovae. Being in the outer disk would mean lower metallicity and perhaps less complex planetary systems. Our location seems neither special nor unusual. Third, the Milky Way's satellite system, while typical in number, includes the unusually massive Magellanic Clouds. These are the most massive satellites of any nearby spiral galaxy. Their interaction with the Milky Way may be enhancing star formation and creating unique structures, like the Magellanic Stream, a trail of gas stripped from the Magellanic Clouds. Fourth, observations suggest the Milky Way is near the massive end of the spiral galaxy distribution. While not an extreme outlier, we're larger and more massive than the median spiral galaxy. This affects what we consider typical. Fifth, upcoming mergers matter. The Milky Way-Andromeda merger, occurring in 4 to 5 billion years, will transform our galaxy. Many spirals face much longer timescales before major mergers, if ever. Our local group environment sets up this relatively early merger. Sixth, detailed studies of the Milky Way's chemical abundances and stellar populations reveal complexity that we simply cannot observe in distant galaxies. This doesn't make the Milky Way unusual, it makes it uniquely well-studied. Other galaxies likely harbor similar complexity that we cannot resolve. So how does the Milky Way compare to other spiral galaxies? In most ways, remarkably typical. Our galaxy is large, but not giant, with a stellar mass around 60 billion solar masses and diameter about 100,000 light-years. We're a barred spiral with a modest bulge and moderately open spiral arms, a common galaxy type. Our star formation rate of 1 to 2 solar masses per year is normal for our size. Our metallicity follows expected trends. Our rotation curve shows the same flat profile indicating dark matter that all spirals display. We have a typical satellite system, a typical black hole given our bulge mass, and typical stellar populations and chemical abundances. Our environment, a small galaxy group, is the most common setting for spiral galaxies. Where the Milky Way might be slightly unusual, our massive satellite galaxies, the Magellanic Clouds, are larger than typical satellites. Our upcoming merger with Andromeda is relatively soon compared to typical timescales. Our local group environment sets up this relatively early merger. Our location near the upper end of the spiral galaxy distribution